Hey everyone, it's Dr. Walker. Let's look at the first example from video 57C on calculating moments of inertia of extended rigid objects. This example, we're finding the moment of inertia of a uniform rod. It has a length L and a mass M. You can see it lies along the x-axis and it's centered about the y-axis. So for part A, we're letting the y-axis be the axis of rotation, so it's rotating about this axis, and we want to find the moment of inertia. Well, what we can do is we can write down the expression for the moment of inertia. I equals the integral of r squared dm. And then we have to make our substitution. We just learned in the video that when an object is a line, so one-dimensional, we make the substitution lambda dx for the dm. That way we can integrate over the length. What we're doing is we're splitting up the rod into a bunch of little segments that have a length dx. They each have a mass dm and a length dx. We can also write our linear mass density as mass per length. So lambda is m per L dx. Okay, so remember that r is a distance from your axis of rotation to your little mass element. That is a distance r. So in this case, can you see what the distance r is equal to? Well, it's always going to be the x position. The distance from the origin to the dx is just x. So we can make the substitution that r squared is equal to x squared. We can also take the m over L outside of the integral because it's a constant. So we're going to have the integral of x squared dx. And what are going to be our limits of integration? Right? Imagine that you have a little mass element on this side, little mass element on this side. Your x value is going to go from negative L over 2 all the way up to L over 2. So that's the trick when doing these types of problems. You make the substitution for your little mass element in terms of length, area, or volume, and then you figure out, okay, what are the limits of integration? It's helpful to visualize the little mass elements. You can visualize more than one along the length of the rod, just so you can see what the limits of integration are. Now we're ready to perform our integral. We're going to have x cubed over 3 when we integrate, and then we're going to plug in the limits. Negative L over 2 to L over 2. So when we plug in these limits, we're going to have m over L. We're going to have, when we put in L over 2, we're going to get L cubed over 8. Actually, the factor of 3 here, I'm just going to take it out. So we're going to have L cubed over 8 minus a negative L cubed over 8 when we plug in our limits. So that is going to give us m over 3L times 2L cubed over 8. So we can go ahead and cancel out one of the L's to get L squared here. We're going to get 2ml squared over 24, which is equal to ml squared over 12, or 1/12 ml squared. If you go back to the table with all of our moments of inertia, this was provided in the table when you spin a rod along the central axis. We get 1/12 ml squared. Now for the second part of this problem. What about if we rotate the rod about this y prime axis, which is at the end of the rod? Is the rod going to be easier or harder to rotate? It's going to be harder to rotate, right? Because we have more mass that is further away from the rod. So that means the moment of inertia is going to be a bigger number. In order to do this one, we just need to use the parallel axis theorem. Let's do part B. Let's write down the parallel axis theorem. I equals the moment of inertia that goes through the center of mass plus md squared. We just found the moment of inertia through the center was 1/12 ml squared. Now we have to add md squared. Remember, d is the perpendicular distance between the central axis and the new axis. So that d happens to be half the length of the rod, L over 2. So when we do this, we're going to get 1/12 ml squared plus 1/4 ml squared. When we add these two together, that's going to give us 1/3 ml squared. So as we expect, we have a higher moment of inertia when we rotate about one end of it. And once again, this is the same expression that we found in that table.